Hello there, and welcome back to our Chemistry for Engineers class. This is chapter 2, and we're going to be looking at atoms and molecules. All right, so first of all, let's take a look at a few different things. So the first thing that we're going to look at is we're going to be looking at the concept of polymers. And what polymer means is poly from the root for many and mer for your particles or your molecules. So whenever you see that poly, okay, so a monomer means one and a polymer means many. Okay. So monomers are small molecules linked together within polymers. So it's the small piece of the molecule. Okay. And the polymer backbone is this long chain that we're going to be repeating. So one, two, three. And we'll see that with ethylene. All right, so let's take a look at basically this polyethylene. It's used in everyday objects, and it's probably one of the most common polymers that we have out there. And it's made up of it can be listed as a couple different things. You've got, in this case, we've got polyethylene, and then we have a polyvinyl chloride, which is still basically a polyethylene, but with chlorine on it or chloride on it. Okay. And then you have polyacetylene in here as well, which takes our acetylene and brings it together. Now, each one of these has very distinct properties that can be used in a lot of different things, very useful. So now let's take a look at something. Let's take a step back and look at our compounds. And even before that, take a look at our atoms. So first of all, we have the fact that matter is composed of atoms. So matter is made up of atoms, okay? Atoms have a nucleus, and that nucleus is right here in the center of our picture, okay? It contains protons, okay, and neutrons. And those are also right here in the nucleus, and they're stuck together really, really, really tightly. And then what we have is we have these electrons in the cloud, and these have a negative charge. And here's our electron cloud all out here, okay? And when we get a little farther in, we'll be talking a little bit more about what these look like. But for now, the electrons are depicted as clouds of negative charge surrounding the nucleus. And it's not really a cloud, it's just that the electrons are moving so fast that we can't actually predict where they are. And they're moving so fast that it's sort of like they're everywhere all at once. And all of the density of our nucleus, of our atom, is going to be right here in the center. Okay, so now let's take a look at how we identify our mass for our atoms. So first of all, let's take a look at a periodic table. Hopefully, actually, this is a good time for me to tell you to get out your periodic table and take a look at that. Okay, so here in our periodic table, let's go ahead and take a look at an element. We'll look at helium. Okay. And helium is right here, and it says it has an HE right here, and it has the word helium on the top, and then it has a 2, okay? And then down below it says 4.0026. Okay, so let's take a look at what this means. First of all, right here is the name, okay? And right here is the atomic number. And that atomic number is equal to the number of protons. And in the neutral atom, also the number of electrons. Okay. And then here we have, and we'll be coming back to this, we have this 4.0026. This is the mass. And the mass is equal to the number of protons plus the number of neutrons, and that's a weighted average. So in this, you'd be looking at 2 protons and 2 neutrons, basically. Okay. And then right here, you have your symbol. Okay. All right. So the atomic number right here, we'll come back to that. The atomic number right here is equal to your number of protons. And when it's neutral, your number of electrons as well. Okay. And then here we have, again, we have our mass number, and it is the protons plus the neutrons. And that's what we've got right here. Okay. And let me make that a little bit clearer. Here's that atomic number right here. Okay. All right. So now let's take a look at the conversion. So the conversion between an atomic mass unit or an AMU is 1 atomic mass unit is equal to 1.6605 times 10 to the negative 24th grams. And the atomic mass unit is basically just a made up value. And where it comes from is that 12 AMUs is the exact mass of, so the exact mass of 1 carbon 12 atom. Okay, so it's totally a made up value. And we'll talk about what a carbon 12 atom is in a minute. Now, taking a look here, let's go ahead and think about converting these. So how much does each one of these have? So for our proton, okay, and sometimes we abbreviate sorry. All right. So sometimes we abbreviate a proton as P plus, and it's listed as having a mass of 1.007 AMUs. Now, to find out the mass of a proton in grams, we would say 1 AMU is equal to this value up here, 1.6605 times 10 to the negative 24th grams. And that means that the mass of a proton, so here you can see we have 4 significant figures. So the mass of a proton then is 1.672 times 10 to the negative 24th grams. Okay, now I would encourage you at this point to pause our video and find on your own the mass of the electron and the mass of the neutron. Okay, so go ahead and pause that and find it on your own. And then what I'm going to do is I'm going to show the math then for you. Okay, so that math for the electron. So with the electron here, I actually have only the 2 significant figures listed. And so that would be 0.00055 AMUs. And notice that that protons and neutrons are about 2,000 times heavier than electrons. These are quite small. Okay. And again, I use this same conversion. 1 AMU is 1.6605 times 10 to the negative 24th grams. Okay. And then when you put that into your calculator and get 2 significant figures, you will have 9.1 times 10 to the negative 28 grams. So that's pretty drastic. I know it's hard to see in this, but it's pretty amazing. Okay, so let's look at one more. Let's do our neutrons down here. And neutrons are only a tiny bit heavier than protons, okay? And so we have 1.009 atomic mass units, okay? And I'm going to squish this in. And again, that conversion, one atomic mass unit goes with 1.6605 times 10 to the negative 24th grams. Okay. And again, we can have four significant figures from our beginning here. And so this becomes 1.675 times 10 to the negative 24 grams. Okay. So you may need that later on homework or on your quiz. Okay. All right. So good. Again, if you're having trouble with your calculator, let me know during our recitation in class. All right, so let's take a look at isotopes. So isotopes of are atoms of an element that have different numbers of neutrons in their nucleus. Okay, and an isotopic abundance is the percentage describing the relative amounts of each isotope. Okay, so in this case, when we're looking at it right here, this is for carbon. Okay, whoops, spell carbon correctly. All right, and this right here is showing carbon 12. And carbon 12 has 6 protons and 6 neutrons. And then right over here, and you can see that carbon 12 takes up almost all of our carbon, but right here, you can see carbon 13. And carbon 13 has 6 protons because the number of protons never changes. That's always exactly the same. This has 6 protons and 7 neutrons. And that's because this 13 here is the mass number. So you might also see this written like this, see 13. And you might also see your carbon 12 listed like this. Okay. All right, so now let's take a look at what's going on in a little bit more detail. So here we have a couple of things. So now let's take a look at our atomic symbols. We're going to be writing our atomic symbols in this form right here. Okay, and in that, let's take a look at what goes with what. So first of all, we have our X value here. Okay, and that is the atomic symbol for the element. So in carbon 12, that symbol is a C. Okay, and next let's take a look here at this Z value. The Z value here is the atomic number or the number of protons. Okay, and in carbon, that's 6. So let me and draw real quick what you would. So if you're looking at your periodic table again, okay, so the box for carbon on your periodic table, make sure you're finding it, has a big C in the middle here and the word carbon here. Okay, and then it has a 6 right here and 12.011 down here. Okay, so this value, okay, now that we're looking at this, let's take a look at where that is. This 6 right here is your Z value. Okay, and this C right here is your symbol here, your X. And this 12, though, this can change. Okay, so remember on the previous slide, we showed carbon 13 as well. Okay, so we showed carbon 13. So if we were doing carbon 13 or C13, this would still be a 6. And this one would have that 6 protons and 7 neutrons. So the number up at the top, the mass number is equal to the protons plus the neutrons. Okay, so that's right here. That mass number is here. And then I have the mass number here as well. Okay, and here is your A. That's your mass number up here. Okay. All right, so let me show you a few. So what I want you to do is pause the video and work this out for nitrogen, oxygen, and calcium. And I am going to go ahead and show you those. Okay, so let's start fresh. So first of all, for nitrogen 15, our symbol. So you have to find these on the periodic table and don't just copy down what I'm doing. You really need to pause the video and you need to find these for yourself on the periodic table. If you don't do that, you're not going to know how to do it in your homework and on the quiz and on the test. Okay, so in here, I find nitrogen and it tells me that my symbol is an N and my atomic number is a 7. Okay. And it's 15. Okay. That goes right here for my mass number. And then for this, that means that I have 7 protons and I have 7 electrons and I have 8 neutrons because 7 plus 8 equals 15. Okay. So now let's go ahead and we'll look at the next one. Now, if you needed help on that one, our next one here is oxygen 17. So again, pause the video and see if you can find it on your own. Okay, we have oxygen 17. Okay, so I find the symbol for oxygen and it's an O. All right. And then this 17 means that my mass number is 17 right there. And my atomic number is an 8. And what that means is that I have 8 protons and 8 electrons. Okay. And I have, so in order to find my number of neutrons, I take that 17 minus 8 and I will get 9. And that is my number of neutrons. All right. So now let's do our last one here. And for calcium 46. All right. And again, you have to find calcium on your periodic table, and you will see that your symbol is a Ca. That is my mass number for this isotope. Now you'll notice sometimes this doesn't match the value on your periodic table, and those because those are weighted averages. Okay, we'll be showing you how to look at that a little later. Okay, but it tells me that my atomic number is 20. Okay, and so that means that I have 20 protons and 20 electrons. And to find my neutrons, I do 46 minus 20. And for this particular isotope, I see that there are 26 neutrons. Okay, so hopefully that wasn't too bad. All right. Slide 8. Okay, now what we're doing is we're looking at our atomic masses in a little bit more detail. All right, and this is where I said, let's get to that a little bit later. So every isotope has its own mass number because it has its own number of neutrons. But in this case, what we're doing is we're going to say, okay, well, how much is each one? So let's take a look at this. The atomic weight of an element is the average of the atomic masses, but it's not an exact average. It's what we would call a weighted average. Okay. It's specifically a weight average of the atomic masses. And the way that we find that is we take the mass here times the percent, the abundance. This is the percent abundance of it as a decimal. Okay, so this is times the percent as a decimal. And it gives you the mass right here of that isotope. So we can see the carbon 12 makes up 98.93% of all carbon. Okay, now carbon 13 makes up 1.07% of all carbon. And so when we change that, we get our percent as a decimal here. Here is the mass of carbon 13, and you'll notice that it's not exactly 13. And when we multiply those together, then we get the mass of the carbon 13 isotope. And then in the end, we add them together. All right. So sometimes what we'll do is we'll put this all together a little separately. So let's take a look at a compound here, and we can see that the chlorine present in PVC is made up of chlorine 35 and chlorine 37. So let's take a look at what we're doing here. So first of all, we have chlorine 35. So I'm going to set that up just like that. And then it also tells us that we have chlorine 37, like this. Now, if I look at my periodic table, that's my next step here, I see that chlorine is number 17. Okay, so I'm going to put a 17 down here and here. Okay, and it's always helpful to kind of figure out what we're working with. Okay, now let's take a look. Chlorine 35 has a mass of 34.97 atomic mass units. And it makes up 75.77% of all carbon. So what now I'm going to do right here is I'm going to turn that into a decimal 0.7577. Okay. And we do that by moving this twice, 1, 2. Chlorine 37, and it tells us that our mass for chlorine 37, let me kind of draw a little line here so that we can see where we are in the middle. Okay. Our mass for chlorine 37 is 36.95 atomic mass units. And we want to know the atomic weight of chlorine. Okay. And this is your average atomic weight of chlorine. Okay. They did not give us a percentage. And that's because all mass percents have to add to 100. And you can actually see that on your notes template in there. So in order to find the mass here, what I'm going to do is I'm going to say 100 minus the mass, minus the percent that we had before, 75.77. Okay, and that's give me a percentage of 24.23%. And I need to convert that to a decimal. Okay, and again, you convert that to a decimal by changing this twice. And you get 0.2423 for that. Okay, now let's go ahead and take a look at our whole thing. Okay, so we can put these together and you can say, okay, it's for your first isotope for chlorine 35, it's your mass of 34.97 times your percentage here as a decimal, 0.7577. And we're going to call this our abundance. Okay, plus that same information for chlorine 37. Okay, and that is 36.95 atomic mass units times the abundance here. So again, this is your mass times your abundance. And that is 0.2423. Okay. And when I work through all of this, what I will get is 35.45 atomic mass units. Okay. And that is the average atomic weight of chlorine. All right. Now, okay. Go. Okay, so now let's take a look at some ions. Ions are formed when an atom has lost or gained electrons. So a cation, and I always remember this because the T looks like a plus, is a positive ion. And that means that it has lost electrons. The number of protons do not change, okay? So protons do not change. Only the electrons. So the protons always match your atomic number. So let's take a look at cations here for a moment. So in a positive ion here. All right. So first of all, sodium forms a cation. Okay. And let's take a look at sodium 22. So neutral sodium 22 is Na with a 22 up here and an 11 here, and it has 11 protons and 11 electrons. And we'll go ahead and stop there. Now, sodium loses one electron to become Na plus. So you could write sodium 2 as a cation like this and say Na2211. And now we're going to put a plus symbol up here. And that's you've lost one electron. You have one extra proton, basically. And so now you have 11 protons and 10 electrons. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 positive charges. Those are your protons, but you've lost one electron. And so you only have 10 electrons, and that's where that extra positive charge comes from. Now, in an anion, anions are negative ions, and we have, in this case, we have gained electrons, okay? And a good example of an anion that has gained electrons is chlorine, all right? So let's look specifically at the chlorine 35 that we had in that last slide. And so you have Cl 35, and it is always going to have a 17 right down here, okay? Now, chlorine, and when you do that, you're going to have 17 protons and 17 electrons. Now, chlorine gains one electron, and this is really interesting, okay? When it gains one electron, it becomes chloride. Okay, we don't actually change the name for cations, but we do for anions. And it'll be a Cl minus. So if we were going to do this for chloride, we would have the same thing. So we would have Cl minus now and 35 and 17. And in this case, now we have 17 protons and we've gained an electron. So now we have 18 electrons. Okay. So a monatomic ion is derived from a single ion. And examples of that would be that Na plus that we have above or a Cl minus. Now you all have this, hopefully you can see it up there. This is the constants and conversions and formulas and ion list. And this is on the back of your periodic table. You already know that you've got constants and conversions up there, but you also have an ion list there. It's the same chart that we use for general chemistry, Chem 120. And these are standard basically all the way through. So you'll see that you have monatomic ions there, but then you also have polyatomic ions. And these are derived from a group of atoms with an overall charge. So basically it's kind of like a molecule. So for example, you might have ammonium. This is one of our only polyatomic cations, and it's NH4. So 1 nitrogen and 4 hydrogens, and the whole thing carries a +1 charge. Another example of a polyatomic ion might be chlorate. And chlorate has one chlorine and three oxygens, and the whole thing together has a 1- charge on it. Okay, so those are some examples of how you would form these. And we're going to talk more about those molecular formulas on the next slide. All right, so chemical formulas, and this is what we were looking at just a minute ago. Okay, so it says that we have, okay, so chemical formulas describe a compound in terms of the elements that the compound contains. All right, so a chemical compound is a pure substance, and it's made up of atoms of two or more elements joined together by chemical bonds. So molecular formulas show the exact number of elements in a compound, and empirical formulas show those in their simplest ratios. And that is actually really important because when we use something called a mass spectrometer, we put a small amount of chemical into the mass spec. And what happens is that the mass spectrometer spits you out only the empirical formula, or only the ratio of elements. So it's really important that we can go between molecular formulas and empirical formulas and molecular formulas, because sometimes our tools can only give us an empirical formula. Excuse me. All right, so some examples of these molecular formulas and empirical formulas is, for example, let's take a look at water. So water looks like this, and you will learn how to draw these in a later chapter. The molecular formula for this is H2O. Now, you can reduce this. 2-to-1 ratio is as small as you can go. So that means that the empirical formula for water is still just H2O. Now, the next example that I have here is HOOH. Okay. Is hydrogen peroxide, and it's H2O2 for hydrogen peroxide. Now, the empirical formula for this is a simple ratio for this, and it would be HO. Okay. So the next one that I want to show here is benzene, and benzene has like this, and there's a hydrogen on each one. Okay. And you can't draw these yet because you're not there yet, but that's okay. Now, this is benzene. It's a very common solvent, and benzene is C6H6, and the empirical formula for that would be CH. Okay. So let's take a quick look at trying to figure out where I am. Here we go. So this gives you some ideas here for molecular formulas to empirical formulas. Okay. So here what we have is we have the molecular formula for ethylene, okay? And ethylene is C2H4, and the empirical formula for ethylene is CH2. Okay. And polyethylene can be written as the C2H2, CH2N. And that's because what we do with this is we basically string these together to make a long chain and for polyethylene. And one of the things that we'll be doing later is we'll be learning how to basically create this polyethylene chain. Okay, so again, just looking at this, the actual ethylene is C2H4, and that is your molecular formula. And if we were going to make the empirical formula for that, we would write CH2. Okay. So now let's take a look at our different kinds of bonding. and then we'll take a break. Okay. So first of all, categories and chemical bonding. So first of all, we have ionic bonding. Okay. And when we have ionic bonding, we have oppositely charged ions that are held together to form this extended array or this lattice structure. Okay. And so there's only ions here. So Na plus dot 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 to Cl minus dot 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 to Na plus dot dot dot. Okay, Cl minus, and it just keeps going. Oops, that shouldn't be. And then they're not actual bonds. That's the thing. So notice that I'm using dots here to show this. So when you have these dots, you'll notice that the dots are connecting your negatives to your positives. Okay, metallic bonding, we'll get to that a little bit differently. When you have metallic bonding is going to be completely different. So this is only metals, and there are no ions because metals only form positive ions, and you can only have ionic compounds when they're balanced. Okay, so when you're working with your metals here, you have your nuclei and some of the electrons, the core electrons. So the nuclei and the core electrons form this lattice structure again for your metals, and your valence electrons basically move freely throughout the whole array. And that's one of the reasons that it can be malleable. It's one of the reasons that it conducts electricity. And we'll get to that a little bit more later. The last type of bonding that we want to introduce here are covalent bonds. And these have electrons that are shared between pairs of atoms rather than donated from one another. And the drawings that I had for the ethylene and the water on the previous slides are great examples of covalent bonds. And the thing to remember here is that there are no ions. Okay. So when you're working with a covalent compound or a molecule, you do not have any ions. Here's a great another picture of our ionic bonding. Okay. And here you can see that we have some examples here. So sodium has one valence electron right here, and chlorine has one gap right here. And so what happens is this sodium, this extra electron in the sodium fills the gap here. Okay, and here you can see it right here, and you can see now that there's nothing on the sodium. But what that does is that creates a positive and a negative charge, and they're just sort of held together because positives and negatives are attracted to each other. Sodium makes this great cubic structure, and it just basically goes on forever and ever, or until you get to the end of the grain of salt. So when you look at a single grain of salt, what you're really looking at is you're looking at a gigantic lattice structure with millions, if not billions, of ions all stuck together like that in a single grain of your salt. Okay. Now here's that metallic bonding I promised. Okay. In metallic bonding, the nucleus and the inner electrons, or your core electrons, which you'll learn more about later, are basically these little positive centers. Okay. And right here is your nucleus and your cores. And then you've got this blue sea out here where you've got some random little negatives floating around all through it. And they move freely through all of it. Okay, so here you've got them just floating around this sea of negative electrons. Okay, so the positively charged metal nuclei are arranged in their own lattice structures, and we'll get to the very specific lattices. It's not always cubic. And then the electrons, or the valence electrons, these are your valence electrons, are going to move freely throughout the whole lattice. And this free movement is what allows our metals to conduct electricity. All right, now let's take a look at covalent bonds. Okay, in covalent bonds, the electrons, where I got to look at my own notes here. All right, in covalent bonds, electrons are shared in pairs. I think you might not be able to see what this says. So if you can't see what this says up here, it says electrons are shared in pairs. Okay, for filling in your notes template. And covalent compounds form distinct molecules, not lattice structures. Okay, so you can see here that the water molecule is here. You can have one water molecule. So they're not lattice structures. You can have one propane molecule. You can have one carbon dioxide molecule. Okay, and they're shared in different amounts of pairs. Okay, so you can have one pair holding a single bond, and that's this water molecule here, okay? And each one of these has one pair of electrons, okay? And then you can see that you have this double bond here, the two pairs for a double bond. And that's what you have here with your carbon dioxide. And you can see right here, there are two pairs of electrons here, or 4 electrons. Just like up in here, you have 2 electrons or one pair. And then lastly, you have this 3 pairs of electrons that can form triple bonds. Okay, and a good example of that is nitrogen gas. And nitrogen gas has a triple bond between it, like this. And that forms 3 pairs of electrons or 6 electrons in between. Often there's a lot of different things that go into it, but usually double and triple bonds are stronger bonds than single bonds. Now let's take a look at our periodic table. Okay, so what I want you to do now is I want you to go ahead and get out your periodic table. Okay, and you're going to write on your periodic table. Okay, and you'll notice on the notes template that I said pull out your periodic table. Here I have this color coded, and when you come into class, when we do recitation, I will have some materials available so that you can color code your periodic table to match mine if you so desire. Okay, but let's take a look at what these are going to be. So our alkali metals are group 1, and that means column 1 at the top. And our alkali metals are lithium and sodium and potassium, rubidium, cesium, and francium. Okay. Now our alkaline earth our alkaline earth metals are column 2, and these are beryllium, magnesium, calcium, strontium, barium, and radium. Okay. Next, we have our halogens. Now we're going all the way over to column 17, also called 7A, and it's that the numbers actually correspond here with the number of valence electrons, which we'll get to more later. The halogens are fluorine and chlorine and bromine and iodine and astatine. And technically, I guess tennessine, but we don't do those. Now, next we have our noble gases. Okay. Now, our noble gases or rare gases, these are going to be very specific, and they have full octets or duets. And our noble gases are helium, neon, argon, krypton, xenon, radon, and oganesson. And those are group 18, so columns here. Now let's take a quick moment here and look at these in a little bit more detail. One thing to note here is that alkali metals can be neutral, but they always form +1 cations. Your alkaline earth metals can be neutral, but when they form cations, they form +2 cations. Your halogens can be neutral, but when they form anions, they form -1 anion. So you can always kind of remember that. Now we have some different regions here. You'll notice groups 1 and 2 and 13 to 18 are what we would call main group. Okay, so this is our S block and P block. And we'll talk more about those later. Whoops. S block and P block. Groups 3 through 12 are what we would call transition metals. And so this is scandium to zinc and down to lawrencium and copernicium. Oh my goodness. Okay, so that makes up that block there. And this, you'll learn more about this later, but this is known as the D block. Okay, the lanthanides and the actinides appear below the rest of the table, and that you can see that they're sandwiched between the P block and the S block. And these will later know these as our F block. Okay, let's take a look here. All right, so I have a different periodic table to show you in class again, but this is just a little bit of a nice color-coded copy that we have here. Okay, now the thing that we're going to remember here is that the lanthanides begin with number 57, and they go through 70. So on your periodic table is better in that it shows these right up here. So just you'll want to place these here. So number 71 goes here, and it's lutetium, okay? And number 103 goes here, and it is lawrencium, okay? And your these are your F blocks. And here you have your lanthanides here. And here you have your actinides. Okay. And you can see here, this is going to help you match these. So here you've got your alkali metals right here, and you can color code them here. Okay, and then here you have your alkaline earth metals in yellow, and you can color code them there. Okay, and then you can see all the way over here, you have your reactive nonmetals in green, your noble gases in purple, basically post-transition metals in blue, your transition metals here. So feel free to do that. The next thing that I want you to do also, though, is let's take a look and draw on your periodic table your metals line. All right, and your metals line is going to go right in here. Like that. Okay, so everything over here plus hydrogen, these are all nonmetals. Okay, and down here on this side of things, we have metals. Okay, so I'm just going to draw a nice heavy bar here showing all of these. Okay, so these are your nonmetals, and everything else is a metal. All right, so now let's take a look at what some of these are going to be. All right, and we have some definitions or some things to add in here to describe things. First of all, metals are shiny, malleable, and ductile. They conduct electricity, and they tend to form cations. Okay, so that's a really important thing here. Metals form cations, which means metals are only going to form positive ions, not negative ions. Non-metals are not shiny, they're not malleable, and they're not ductile. They make up a lot of your organics, they do not conduct electricity and they tend to form anions. Okay, so remember that means that they are going to be negative. Okay. Okay. Or semi-metals tend to have chemical properties that are between metals and non-metals. Some of the metalloids are more metallic and some of the metalloids are more non-metallic. And I'll show you where to draw that line. All right. All right. Now, this slide is going to show you a little bit more specifically. Again, this is similar to what we saw before. Here you can see your metals versus non-metals, and it's very important that you know where those are. And then you've got your metalloids in between. And now remember I said that we have things that are more metallic than non-metallic. And so what I want to do here, again, is just to sort of draw here. You've got your non-metals. And if we were going to separate the metalloids into metals and non-metals, this is how we would draw this. Okay. And everything up here is more of a non-metal. Okay. So if I say, so that means that arsenic would form a negative ion and germanium would form a positive ion. Okay. And that's why you draw that line where you do. All right. I think that is an excellent place for us to take a break. So go ahead and take a little break and come back for part 2 and slide 20.